Imagine, for just a second, that you are standing on a dock right next to a modern cargo ship.
Yeah, which is a pretty imposing sight.
Oh, absolutely. I
Yeah.
mean, you are looking up at a vessel that weighs 100,000 tons, stretching the length of like 3 football fields. It's carrying thousands of shipping containers across the open
It
ocean.
really is a marvel of heavy industry.
Yeah.
Just massive amounts of steel and diesel.
Right. But to really understand what you are looking at today, you need to completely shift your perspective. You aren't just looking at a ship. You are looking at a 100,000-ton floating computer.
Exactly.
And I guess that brings us to the mission of our deep dive today. We are going to explore the hidden digital vulnerabilities of the global maritime industry.
It is a massive shift in how we need to think about maritime safety, really. Because, think about it. When your personal laptop at home gets a virus, what is the worst case scenario usually?
You lose a file. Or maybe you have to, buy a new hard drive.
Right. But when a modern cargo ship gets a virus, the stakes scale up so dramatically, you could be looking at a catastrophic collision at sea.
Oh, wow.
Yeah, or the total loss of the vessel, or even a massive environmental disaster. So the digital failure literally becomes a physical crisis.
I like to compare this to the transition we've seen with smart homes, just on a much, much larger scale. Like, it is one thing if a hacker gets into your smart fridge and, I don't know, messes with the ice maker.
Or annoying, sure.
Yeah, exactly. But it is an entirely different level of terrifying if they can hack into a modern skyscraper's elevator system while you are moving inside it. The stakes are physical, not just digital.
That is a great way to frame it.
And to guide us through this whole complex web today, we're using a single, incredibly comprehensive source. It's called the Guidelines on Cybersecurity on Board Ships version 4, published in 2020.
Which is a huge deal.
It is. This isn't some fringe theory document. It is supported by the biggest heavyweights in the industry. We're talking BIMCO, the International Chamber of Shipping, the World Shipping Council. I mean, these are the organizations that literally keep global trade afloat.
And what really stands out in these guidelines is that they aren't just raising a theoretical alarm about some distant future.
Right.
They provide a really detailed blueprint of how vulnerable these vessels are right now, specifically because of how rapidly the industry is digitizing.
Because they want to be more efficient, right?
Exactly. Shipping companies operate on incredibly thin margins. They're constantly seeking operational efficiency, fuel savings, better sustainability metrics, and to get that efficiency, they rely on real-time data.
So they have to connect everything.
Yeah. To get that data from the middle of the ocean all the way back to corporate headquarters, you have to connect the ship's physical systems to the internet via satellite. And the moment you build that bridge, well, you open up massive security holes.
We kind of have to separate the ship's digital brain into two halves to really grasp this, I think. You have IT and OT, information technology, versus operational technology.
Which is a crucial distinction.
Right. I think everyone is pretty familiar with IT. That is your emails, the cargo manifests, the crew payroll data, the administrative stuff. But OT, operational technology, that is the hardware and the software that actually monitors and controls the physical devices on the ship.
The heavy machinery.
Yeah, the main engines, the steering gear, the ballast valves.
And the maritime industry faces these unique, almost paralyzing challenges when it comes to defending that OT. First off, you have a staggering number of stakeholders involved in a single voyage.
Like who?
Well, you have the ship owner, the management company operating it, the charterer renting it, local port agents. It creates this massive gray area regarding who is actually accountable for the network security on any given Tuesday.
That sounds like a logistical nightmare.
It is. But the hardware itself presents an even bigger hurdle. Ships are really expensive assets meant to sail for 20 or 30 years.
So the tech gets old fast.
Exactly. They are riddled with legacy systems running completely obsolete operating systems. And many of those critical OT systems literally cannot be patched or run antivirus software due to this regulatory hurdle called type approval.
Okay, I'm going to need you to explain that one because it sounds totally counterintuitive. If there's a known security flaw in my phone, the manufacturer pushes a patch and I update it. Are you saying ship owners are like legally prevented from fixing known security bugs?
In many cases, yes. It is basically a regulatory catch-22.
Wow.
In maritime law, critical safety equipment like the electronic chart displays or the power management system has to be rigorously certified or type approved to guarantee it works exactly as designed under extreme conditions.
Okay, makes sense.
But if a shipping company decides to update the underlying software or install a background antivirus program, they alter the system's baseline configuration.
Which means
Doing so instantly voids the safety certification.
you are kidding.
Nope. The equipment is no longer considered seaworthy by the regulators. So you end up with critical navigation systems that are legally required to stay frozen in time. They have to remain exactly the way they were when they were installed, even if a massive, easily exploitable cyber vulnerability is discovered the very next day.
Let me make sure I'm grasping the real-world implication here.
Yeah.
If the IT network gets hacked, maybe a company loses a cargo manifest or some sensitive corporate emails are leaked. Bad, but, it's a corporate headache.
Right.
But if the OT network gets hacked because it's running a 20-year-old operating system that legally cannot be updated, the steering wheel effectively develops a mind of its own.
Yes, you lose control of the physical vessel. And historically, this wasn't a problem because those OT systems were standalone. The engine control computer was literally just a box in the engine room.
Not connected to anything.
Exactly. But as we discussed with the push for efficiency, those systems are now increasingly integrated with the IT systems, so the shore office can monitor fuel consumption. The line between the administrative computer and the engine computer blurs.
So a vulnerability in the captain's email inbox can suddenly become a direct digital gateway to the propeller.
That is exactly what happens.
I am still hung up on how these breaches actually happen in practice, though. My mind instantly goes to a Hollywood movie. I am picturing some mastermind hacker in a dark room halfway across the world, typing furiously to take over a super tanker in the South China Sea.
Well, targeted state-sponsored attacks do occur, obviously.
Yeah.
But if we look at the reality painted by the guidelines, the most common threat to a ship is vastly more mundane.
Really?
Yeah, it is not an evil genius in a hoodie. It is simple, human error, accidental actors, and just the chaotic environment of a modern seaport.
The source has these incredible real-world anecdotes that highlight this perfectly. There is this one story about a bunker surveyor. For context, a dry bulk ship is in port, and they just finished taking on fuel, which in the maritime world is called bunkering.
Right.
So a local surveyor boards the ship to verify the fuel amounts. He walks into the engine control room with a clipboard and just asks the crew if he can use their computer to print out a document for a signature.
Seems harmless enough.
It is the most normal, everyday request you can imagine in a business setting. So he plugs his cheap promotional USB drive into the ship's computer. Without knowing it, he introduces malware straight into the ship's administrative network.
And the crew didn't even know it happened.
Nope. They just started complaining about a sluggish computer issue weeks later, and a completely separate cyber assessment eventually found the malware.
That single moment, just asking to print a PDF, bypasses millions of dollars of potential perimeter security. You can have the best satellite firewalls in the world, but they are useless if a visitor physically walks a virus past them and plugs it directly into the motherboard.
It's like leaving the front door wide open.
Exactly. But the threat isn't just clueless visitors. It gets even more complicated when you look at intentional authorized software maintenance.
Oh, the Gremlins store.
Yes. The guidelines share this incident involving a ship under active pilotage. Pilotage means the ship is navigating through a highly difficult, congested waterway, relying on a local expert who is temporarily boarded to guide them.
High-stakes maneuvering.
Very high stakes. And in the middle of this, the ship's electronic charts and voyage computers start completely crashing. The screens just go black.
And the master of the ship, the captain, just thought the ship had gremlins. He thought it was just a quirky mechanical ghost in the machine because old ships have weird electrical hiccups all the time.
Right, he had been complaining about these gremlins to the company for a while. But the root cause wasn't a ghost, and it wasn't a malicious hacker either.
What was it?
The investigation revealed that during a previous port call, the manufacturer's own technical representative came on board to perform a routine, highly recommended navigation software update.
Okay.
The technician installed the new software, but the ship's underlying hardware and operating systems were so outdated they simply couldn't process the new code.
Oh, no.
Yeah. It created a severe conflict, causing the critical navigation systems to reboot themselves randomly during the worst possible moments of navigation.
It is wild to think about. We imagine cybersecurity as this battle of cryptographic algorithms, but a massive vulnerability is literally just a well-meaning technician installing a modern update on an ancient computer.
Exactly.
The guidelines mention another story, too, about a brand new dry bulk ship, a new build, designed from the keel up for completely paperless navigation.
Supposed to be state-of-the-art.
Exactly. But it got delayed from its maiden voyage for days because its electronic chart system, the ECDIS, had a virus.
Just right out of B.
Yeah. At first, the crew just thought it was a standard technical glitch with the new system. They had to fly a specialist technician out, spend hours and hours troubleshooting, only to finally identify the virus. That single delay cost the owner hundreds of thousands of dollars in lost time and port fees.
And the most concerning part of that new build story is that the source of the infection was never even found. The ship was infected before it even left the shipyard.
That's terrifying.
It proves that the attack surface is incredibly broad and extends through the entire supply chain. But, while accidents and gremlins make up a large portion of the incidents, we do have to examine the malicious threat actors.
Right, the actual bad guys.
When criminals, activists, or state-sponsored organizations intentionally target a vessel, they don't just guess passwords. They follow a highly structured playbook.
Let's walk through that playbook, actually. If I'm an attacker, and I don't have the luxury of just walking onto the bridge with an infected USB drive, how do I actually compromise a ship from 1,000 miles away?
So the guidelines break an intentional cyber incident down into 4 main stages. First is the survey, or the reconnaissance phase.
Okay.
Attackers use open sources, social media, or specialized network scanning tools to map their target. They will search LinkedIn to find out the names of the chief engineers. They will look up public maritime databases to see exactly what brand of engine control systems a specific ship uses.
And then what?
Then they literally download the PDF manuals for those systems to study the default passwords.
Wow, just basic research.
Exactly. Second is the delivery phase. This is where they attempt to penetrate the perimeter. They might send a highly tailored phishing email to the captain, spoof a trusted maritime weather website, or even intercept a package being mailed to the ship and swap a legitimate software update USB with an infected one.
Okay. Then come stage 3, the breach. They trick a crew member into clicking a link and they are in. But typically, they only gain access to the lowest hanging fruit, right? Like the administrative network or maybe the crew's Wi-Fi network where they watch movies.
Yeah, at first they're just reading emails or looking at payroll data.
Which brings us to the fourth and arguably most critical stage of an advanced attack. The pivot.
The pivot is everything.
Yeah. Pivoting is a lateral movement technique. An attacker uses an already compromised low-security system as a staging ground to launch an attack against a high-security system on that exact same local network.
Right.
I was trying to visualize this pivoting concept for you, the listener, and it is essentially like a burglar targeting a heavily fortified mansion. They don't walk up to the steel front door and try to pick the complex lock. Instead, they easily break into the flimsy wooden garden shed in the backyard.
It's easy.
Exactly. They don't care about stealing the shovel inside. They break in because they can hide in the shed out of sight and then dig a tunnel directly from the shed into the main house, completely bypassing the heavy front door, the security cameras, and the alarm system.
That's a perfect analogy. The garden shed in this scenario is the crew's entertainment network, and the mansion is the ship's ballast water control system. They target the weakest link to gain a foothold.
And once they are in the mansion,
Once they pivot into those critical OT systems, the potential impact of the hack changes drastically. To help shipping companies categorize and prioritize these different types of risks, the guidelines rely on the CIA model. Not the intelligence agency, obviously, but confidentiality, integrity, and availability.
I want to push back on how this is applied, actually, because it really confused me at first. Confidentiality means keeping data secret. Integrity means ensuring the data hasn't been altered or manipulated by an outsider. And availability means the system and its data are actually accessible when you need to use them.
That's correct.
If a hacker gets into the IT network, say, the human resources database confidentiality is obviously the highest priority. You absolutely do not want hackers reading employee medical records or payroll data.
Oh, of course not.
But the guidelines claim that when dealing with operational technology, confidentiality barely matters. Why wouldn't keeping data secret matter? If I own a shipping company, my engine schematics, my fuel burn rates, that is proprietary information. I don't want a competitor seeing that.
I get why that seems backward. But you are confusing corporate intellectual property, which lives on the IT network, with live operational sensor data, which lives on the OT network.
Oh, okay.
Think about a ship's SCADA system, the supervisory control and data acquisition system that manages the physical electrical power on board. The data flowing through that system is just live readings of voltage, engine temperature, and pump pressure.
Right.
That data isn't a secret. Any oiler or engineer walking through the control room can look up at the analog dials and see the exact same information. The impact of a hacker quietly observing the engine temperature is incredibly low.
Ah, I see. The danger isn't them watching the temperature gauge. The danger is them changing the temperature gauge.
Precisely. That is why integrity and availability are critically high for OT systems. If the integrity of the data is breached, meaning the hacker manipulates the sensor to tell the computer the engine is running cool when it is actually overheating, the system won't trigger the cooling pumps, and you have a physical meltdown waiting to happen.
That is terrifying.
And if availability is lost, meaning the screens go completely black or ransomware locks the system so the crew can't see the power management data at all, the ship might lose propulsion entirely and go dead in the water.
So if the stakes are really that high, and an attacker can tunnel from a casual email directly into the engine control room, how do shipping companies build internal walls to stop them?
The industry relies on two structural concepts: defense in depth and defense in breadth.
Okay, what's the difference?
Defense in depth means you don't just rely on one tough outer shell. You layer multiple redundant security measures. You use firewalls, intrusion detection software, strict password policies, and intense continuous crew training.
Layers of armor.
Exactly. Defense in breadth is about segregating the networks physically or virtually. It is about making sure that the garden shed is completely walled off from the mansion so that even if the entertainment network is compromised, pivoting to the engine network is structurally impossible.
But surely the ultimate foolproof method is just taking the absolute most important systems and completely severing them from the network. Like if the power management system isn't connected to the internet at all, it can't be hacked from afar. It's called an air gap. Problem solved.
An air-gapped system feels like the ultimate defense because it is physically isolated from unsecured networks. But the guidelines completely shatter the myth that an air gap guarantees safety.
Really?
Yeah, and they share a genuinely chilling, real-world story to prove just how vulnerable these isolated systems still are.
Oh, the story of the 875-day worm. It reads like a thriller novel.
It really does.
There is a newly built ship outfitted with a highly critical power management system. And by design, for ultimate security, this system is strictly air-gapped. No internet connection, no external network cables. You would think it is perfectly safe from outside influence.
But during the ship's initial construction, or maybe the early servicing phase in the shipyard, a third-party service provider came on board to perform a routine software installation.
The dreaded USB drive again?
Yep, they used a standard USB flash drive to transfer the files. Unbeknownst to them, that drive contained a highly sophisticated, hidden piece of malware known as a worm.
So the worm infects the air-gapped power management system. But here's the crazy part. It doesn't do anything.
Nothing at all.
It doesn't crash the system or demand a ransom. It just sits there, hidden in the system's active memory, for 875 days, over 2.5 years, just waiting in silence.
It was waiting because it was designed to communicate with a remote command and control server to receive its instructions on what to execute next.
Oh, I see.
The malware is essentially blind and deaf until it gets those orders. For 2.5 years, it was effectively picking up a phone and getting a dead dial tone every single day because of the air gap. It couldn't reach the internet.
Until,
one day, the shipping company's own IT department decided to run a routine vulnerability scan on the ship's systems.
and to run the scan, the IT team temporarily connected that isolated power management system to the internet.
Big mistake.
The moment they established that bridge, the dormant worm woke up. The phone line was finally active, and it immediately tried to call out to its master server to download its payload.
If it had received its instructions, the consequences for the ship's entire power grid could have been catastrophic.
So what happened?
Luckily, the vulnerability scan they were running actually detected the outgoing traffic, and they had to bring in expensive forensic experts to purge the entire system. It highlights that an air gap is only as strong as the physical security surrounding it. If someone can walk onto the bridge and plug a device into an exposed port, your network architecture is largely irrelevant.
I read that and couldn't help but wonder, do they literally need to put physical padlocks on the USB ports on the navigation bridge?
I mean, as extreme or low-tech as it sounds, yes. The guidelines explicitly recommend robust physical security for exposed ports. Blanking them off, sealing them, or literally putting physical locking mechanisms over them.
Padlocks on computers.
Yeah. Physical security is the simplest and often the most effective form of cyber defense for OT systems.
So a shipping company implements firewalls, segregates their networks, slaps physical padlocks on the USB ports, and trains the crew relentlessly. But no matter how high you build the walls, the law of averages dictates that a breach will eventually occur.
It's a matter of when, not if.
Someone will click a clever phishing link, or someone will use a dirty USB drive to print a form. When the screens start flashing red and the alarms start blaring, what is the actual first move?
This requires rigorous contingency planning and incident response. The guidelines outline 4 critical phases for emergency response: preparation, detection and analysis, containment and eradication, and finally, post-incident recovery.
The containment phase is where the guidelines completely contradict human instinct, I feel like.
Oh, absolutely.
If your computer at work suddenly starts acting weird, the mouse is moving on its own, or you get a massive red ransomware pop-up, what do you naturally do? You panic, you reach down, and you rip the power cord out of the wall.
Or you hold down the power button.
Exactly, to force a hard reboot and stop whatever is happening.
Doing that is exactly what you should not do in a forensic digital crime scene. The guidelines are adamant about the forensic dangers of rebooting or powering off a compromised computer system.
Why is turning it off so destructive?
It comes down to how computers store temporary data in volatile memory, also known as RAM. Think of RAM like a whiteboard that the computer uses to do rapid calculation.
Okay, a whiteboard.
The moment you kill the power, the whiteboard is instantly erased. Advanced malware, like the 875-day worm we just discussed, often avoids the hard drive entirely and lives exclusively on that whiteboard in the RAM.
Oh, so if you turn it off.
If you kill the power, you have just permanently destroyed the only evidence of how the malware was operating, where it came from, and what it was trying to do.
You erase the crime scene.
Exactly.
Yeah.
Furthermore, if you reboot a system that is partially infected with ransomware, the boot sequence itself might actually trigger the malicious code to deploy and lock up your backup drives as well.
That is brutal. So you isolate the machine on the network, but you leave it running. However, if things are truly deteriorating, like if the OT system controlling the ship's actual propulsion or steering is compromised, and the physical ship is in immediate danger of running aground, there is an ultimate failsafe discussed in the source material. And it is surprisingly low tech.
The ultimate containment strategy is physically severing the operational technology from the shore networks.
Just cutting the cord.
Literally. The guidelines strongly recommend that ship networks should be intentionally designed so that they can be instantly isolated. You don't want a stressed captain trying to remember a complex string of commands to type into a terminal while the ship is careening off course.
Nobody has time for that.
No. Instead, they suggest designing the hardware so the crew can physically pull a single, explicitly marked cable. Using a brightly colored, odd-colored network cable like bright pink or neon yellow ensures that in a moment of sheer panic, the master of the ship knows exactly which cord to rip out of the server rack to sever the ship from the outside world entirely.
Pulling that pink cable isn't a magic fix, though. When they pull it, the ship instantly loses all connection to shore support. The corporate office loses all their efficiency tracking, the live weather routing updates stop, and the ship is suddenly digitally alone in the ocean.
It's a drastic measure.
It really makes you think about how this fundamentally changes the job of a modern sailor. You are asking men and women who have spent their entire careers trained to navigate massive oceans, manage heavy cargo logistics, and maintain massive diesel machinery to suddenly act as first responders in a high-stakes digital crime scene.
Right, they have to possess the intuition to know the difference between a mechanical gremlin and an active network pivot.
Which is an incredible ask.
It is an immense operational burden. They have to constantly balance physical survival against digital contamination, often while totally out of range of immediate hands-on shore support. The crew is the absolute last line of defense.
So what does this all mean for you, the listener, the next time you see a massive container ship on the horizon? If we synthesize everything we have pulled from these guidelines, the core takeaway is a profound paradox.
It really is.
The relentless digitalization of the maritime industry brings incredible necessary efficiency. It tracks our cargo to the minute, optimizes fuel consumption to save millions, and connects global supply chains seamlessly.
But there is a cost.
Right. It also tethers the physical safety of a 100,000-ton steel vessel to the security of its weakest digital links. The threat might not be a mastermind hacker breaking firewalls. It is often a forgotten default password on a legacy system, an unpatchable operating system, or a busy port visitor just trying to print a document from a dirty USB drive.
And if we look at the trajectory of the entire industry, it raises a deeply provocative question about the future.
What's that?
Well, throughout this entire deep dive, the ultimate defense has repeatedly fallen squarely on the human crew. It relies on a human engineer to notice a physical anomaly on the gauges, a human officer to challenge a visitor carrying a USB on the bridge, a human to physically lock a padlock on a port. Well, or in the absolute worst-case scenario, a human captain standing in the server room ready to literally pull that neon-colored network cable.
Without the crew, the defense just crumbles.
Exactly. But the global supply chain is actively pouring billions of dollars into developing fully autonomous, uncrewed cargo ships.
Wait, really?
Yes. We are currently building vessels that will cross oceans entirely on their own, managed only by remote servers. So, the question we have to leave you with is this. As we remove the human crew for the sake of ultimate efficiency, how exactly do we defend a massive floating supercomputer when there is absolutely no one on board to pull the plug?
Wow. Imagine that smart elevator in the skyscraper plunging down and suddenly realizing there's no emergency stop button left to push. Something to think about the next time you order a package from across the world.